My name is Alvin Marks. I'm an experimentalist, an inventor, and a mathematical physicist, and have experience with quite a number of different technologies over the course of my many years as a researcher and inventor. I've been responsible for the development of polarizing materials, 3D movies, lab television, liquid crystals, super hard coatings, and so forth and so on. And I would say that about 12 years ago, through a chance encounter with a UN official that was interested in supplying the third world with power, particularly in the small villages, I was enthused to try to approach photovoltaics from a novel point of view. He laid down the requirements that it had to be cheap and efficient, and upon studying the existing methods of photovoltaics, I reached the conclusion that a totally new approach was necessary. Well, my background is in the field of physical optics and mathematics, physics, quantum mechanics, and so forth and so on. Basically, I'm a scientist, that's my real interest, but I like to apply science to real problems. The name of the gentleman that I met was in charge of the UN Third World Power Systems, a gentleman by the name of Dr. Ishrat Asmani, Pakistani gentleman, who was also at one time a member of the International Atomic Energy Commission. He said to me at dinner, he said, "Alvin," he says, "I understand you're an inventor." I said, "Yes." He says, "Well, I'm not very happy tonight." He says, "The UN has just canceled my photovoltaic project. We had one set up in the middle of Africa in a small village. It was pumping water. It was supplying refrigeration and light, little electricity for radio and so forth. People there were very, very happy with it, and all the surrounding tribes wanted the same thing. However, the system was very bulky. It was difficult to transport. It was very inefficient and tremendously expensive. And the UN people decided that it was not economically feasible to continue with the project. So in desperation, he turned to me and says, "Alvin," he says, "if you're working on anything, if you propose working on anything new," he says, "work on a new photovoltaic." He says, "It's got to be cheap, it's got to be efficient, and it has to be universally applicable." So I said, "Well, I'll give it some thought." In my background, I've done a lot of work with, during World War II, I was at Harvard and MIT. I studied microwaves and radiation physics, and then I was down in the Naval Research Laboratory for a while. I had the run of the laboratories. I was patent liaison officer for the group, and so I had a lot of knowledge of the physics and properties of light and radiation. I knew that light and microwaves were just difference. The only difference between them basically was one wavelength and energy. So anyway, to make a long story short, I developed a totally new approach. My background being in the field of polarizing materials, I'm a pioneer in the field of polarizing materials, manufactured for 50 years and still doing so in another company. I decided that I was going to break away from what I was doing and devote myself to creating this new polarizing medium. What I concluded basically was that I had to use the same system that was used in the conversion of microwave radiation to electric power. There was a publication put out on research done by Jet Propulsion Laboratories in around 1970 something, 78 I believe it was. It was NASA Tech Brief number 50, I think it was. Anyway, in there it reported on what was called a reptenna, which is an antenna and diode combination, which took microwave radiation and converted it to DC power with 82% efficiency. And since I knew the properties of antennae and antenna arrays, I immediately saw that this was a polarizing material, because when you take a polarizing material, which I'll demonstrate here, is number one, and let me just excuse me for a minute. I'll go around and show you what I mean. Is there a No, no. What you see here is a strip of film, flexible film, as you can see, and it just looks like a piece of gray plastic. But let me just fold it over like this, and you'll see it blocks out the light. This way, it's transparent. Turn it and see why. Okay, now what's going on here? This is a piece of stretch plastic. If you look at the edges of this thing, you'll see that it's pulled away like this. It's really a thin crystal which will only tear in one direction. You can't tear it the other way. So the reason for that is the molecules are all parallel to each other. And these are conductive molecules. So that basically what we have here is a molecular antenna. A molecular antenna, but there are no diodes in it. I immediately recognize that if I want to treat with light and make it into a photovoltaic, I needed a conductive polarizing material which would transmit electricity only in one direction. That was the only requirement. Then you had to have electrodes in it to pick up the, to let the electrons come in, let them come out after they've been generated. Now, I'll show show this to you in a little while. But I want to also tell you, before we get into it any deeper than this, that this does not work as a photovoltaic because the antenna elements, which are conductive polymers basically, are embedded in an insulating medium. There's no way for the electrons to get from one antenna to the other. And there's also no diodes in it, so that's why it doesn't work as a photovoltaic. However, the basic idea was there. I knew from my analogy with microwaves that this certainly would work if we could do it on a molecular scale. Now, before I get into the technical details, I want to just say that I feel that the photovoltaic industry is in the same stage today that the electronics industry was in the early 1950s, where the vacuum tube was the method of rectification and amplification of signals. There were vacuum tube computers, there were vacuum tube television sets, there were vacuum tube radios, and that was the only thing known at that time. And they kept improving the vacuum tube, and things were getting better and better, but there was a limit to which they couldn't get past. The limit of energy required to operate each vacuum tube, the limit whereby you could only get so many of them in a certain amount of space, they were too bulky and so forth and so on. That was the limiting, and also the cost was very great. And the energy requirements were very great. So what happened? All of a sudden, the transistor was invented. And from that point on, the electronics industry took off. And today, it's not recognizable on the basis of what you might expect from the 1950s. It's so vastly improved, and with so many new possibilities, and such exciting new things have happened. I feel that with a polarizing photovoltaic that you can, from the theory, you can predict an 80% efficiency. You can predict a cost of anywhere between 5 and 20 cents per watt instead of minimum $2 at the present time, more like $5 in most cases. So the thing is, this new paradigm will change the whole future of the photovoltaic industry. There's one other thing that was necessary. I realized this about 5 years ago as I was working on it. It seems that there's another limitation on the photovoltaic industry, and that is storage of electric energy. Now, I listened to Dr. Shinsky yesterday and the day before. He's a very delightful man, a very great genius and a wonderful person. but I don't believe that batteries are the ultimate. There has to be something with the storage capabilities, gasoline. If you, I calculated that the equivalent specific energy of gasoline is something like 15 kilowatt hours per kilogram, and I set that as my goal. I'll work through all the different methods of producing electrical storage, batteries, capacitors, and so forth and so on, and found that none of them were able to meet these requirements. I must say one other thing. Back in you see, the U.S. government does have a role, and it had a great role in my life because I've had many contracts from the U.S. government throughout my career as an inventor, and maybe 40 or 50 different contracts over a period of time starting from the 1960s. And I currently have agreements with Argonne National Laboratories on this device. I have an agreement. I just got a contract with the Air Force, and I understand that more contracts will be coming in because people are beginning to realize the potency of my proposal. At any rate, getting back to the storage, which is still a dream. Recently, as a result of support by one of the agencies of the U.S. last year, $250,000, 100,000 went to Cornell, 100,000 went to Texas A&M, and 50,000 to Advanced Research and Development just for consulting. Texas A&M produced the first direct proof, an experimental demonstration of light to electric power using an antenna diode system. And that report is available to qualified people who might want to look at it. It was paid for by one of our secret agencies that I think would have to approve the release of the report. At any rate, the report is available in certain circumstances. But I do have a letter from the Texas A&M reporting this result with great enthusiasm and with considerable excitement. I have that available. I gave a copy of the letter to one of the people here. I'll tell you about him later. Anyway, as a result of, go back to 1947. On the GI Bill, I decided to take some additional postgraduate studies. I studied statistical thermodynamics, Fourier analysis, and some other advanced mathematics things. But I also took a course in quantum mechanics. And I can remember sitting through these classes and being an engineer and scientist, I was very intrigued by the quantum mechanics approach, but I couldn't see the slightest use for it in my work. And there I put that book on the shelf about 30 years ago, I guess it was. And there it stood for 25 years until I started working on an energy storage system. And I found it definitely did have an application to what I wanted to do because I've been working with quantum mechanics in the development of the light electric and the polarizing photovoltaic. So at any rate, I prepared a patent application, filed it, and it has now been reviewed by the Air Force and by the Department of Energy, and there are people that have looked at it that like it very much. They're setting up a conference for me end of this month, hopefully, to carry forward this technology with a good deal of money. Anyway, that's just some of the background, and now I'd like to explain a little bit more. I'm not going to tell you much about the storage system today, because that's still in the patenting stage, and have to keep it under wraps except for under strict confidential agreements. Now, so therefore, I will simply go to the photovoltaic system. Now, there are two of them, basically. One uses nanotechnology, which means a metal on glass. There's no semiconductor necessarily in the thing. The rectification takes place by what is known as a tunnel diode. A tunnel diode is simply two metal surfaces, which are within, say, 25 angstroms of each other. And one surface is coated with a donor material. The other side is coated with an acceptor. For example, one side could be a metal which has a low work function, and I'll explain what a work function means in a moment. And the other side has an acceptor which will accept electrons. The donor easily gives off electrons. The acceptor will easily pick it up. And this only works when the spacing is a critical distance between 15 and 30 angstroms apart. And the need for an accurate nanostructure was the real problem that limited the possibility of that being done. That's why the government chose the National Nanofabrication Laboratory at Cornell to do the work, but even they were unable to get down to the resolution required at that point. It was done in a totally different way by electrochemistry, I guess, by sort of like a lithographic technique at Texas A&M. They were successful in producing a first model that worked. So the principle has been proven in practice. Now we have to perfect it and produce it on a large scale. Although I was aware of the problem for a long time, how to do this. The present methods of nanolithography require that you take a resist, which is a material which will prevent a chemical from attacking a surface. And you make it a line in the resist, and usually by photographic means. And the lines, unfortunately, by photographic means are limited by the wavelength of light down to about, the best they can do is about 1,000 angstroms, which is not accurate enough for our purposes. There's another method of nanolithography which has been used very successfully, and that uses the electron beam lithography, which gives you a much higher resolution. However, even that by itself is not enough if you're using a thick resist. Under those circumstances, I proposed using a monomolecular resist, an atomic or molecular resist, which the electron beam would disturb on the surface. As I go through the slides, I'll show you what I mean, but I just want to describe it to you in words first, so that you'll know what I'm talking about when I come to the slide. With that, it's possible to get angstrom resolution. And now there's one other problem that exists, and when you're trying to produce a large area, suppose we want to make a square meter of solar panel and do it in say 10 seconds. If you did it with a single electron beam, it'd probably take you 50,000 years to do the minute pattern over the entire surface. However, if you have 10 billion electron beams working simultaneously, and you might say that's an impossibility, but it's not. Then you could do the whole thing in 10 seconds, which is what I propose to do. Now, the way to get 10 billion electron beams is to use a lithographed emitter source. That's known as a spin electron source, SPINDT. They're making right up here at Stanford Research Institute, and this is for electron-emitted flat displays. They've used it for that. They have very successfully produced 1,000 by 1,000 array emitters. And now just step that up, you could make it as many as 100,000 in a square meter, and demagnified down in an electron microscope in reverse. It's called a beam runner. And you can produce these patterns simultaneously by scanning the beam with a single electrostatic field, just like you do in a CRT. Now, I have a patent on that. I call it the superceptor. It's an acronym for super submicron electron beam runner. The next step is you've got what you now have is a charge pattern on the surface of a piece of glass, and the charge pattern has atomic resolution because you're dealing with an electron beam. Electron beams will give you, say, 2.5, 3 angstroms resolution, for example, in a typical good electron microscope. And so that technology is well within reach. The next step after that is to utilize that charge pattern and coat it with produce a metal pattern which is the same as the charge pattern. And that, at least in theory, is easy to do. What you do is you simply take what is known as electroless coating. They use the chemical fluids which now deposit, for example, copper or silver or gold or any metal can be deposited, aluminum even, on a flat surface without any electric field. The whole thing is done by an electrolytic solution known as an electroless coating. And that's well known. There's a lot of art on the subject. And what I propose to do is to utilize electroless coatings over these charge patterns and deposit the metal pattern directly and coat a square meter of it without any problem very quickly in a few seconds. That's a general approach which we'll be using. That, so far, is in the future. We're looking for, hopefully, U.S. government funds or corporate funds, grants, private investment, whatever, to get this job done. Eventually, I think this project is going to require something of the order of $100 million to bring to conclusion. We'll be able to make demonstrations probably for a few million, just small size pieces. So that's what I call the LEPCON project, LEPCON. That's for light electric power converter. Long about the same time, since I've been working at polarizers, and let me explain how a polarizer is made according to my process, which has been in production for 50 years and still is. The method that I invented was to take a plastic solution, and such as polyvinyl alcohol, which is a long-chain, water-soluble polymer, very cheap, and dissolve it in an alcohol-water solution, add some iodine, a little hydroiodic acid, and stretch it. Let partially flow it on the surface, form a film, dry it almost completely. It's very, very elastic at that point. You can stretch it out about 8-9 times and form a very thin, stretch-oriented polymer. As you see, it becomes a flat crystal, as I showed you, because it will only tear in one direction, and has very strong polarizing properties, used for all sorts of things: eyeglasses, camera filters, on-glass screens, and so forth and so on. Vast market. Now it's expanding into the flat television screen, where there's $250 million market for that. And so the field of polarization has grown from a gleam in my eye to a huge industry. Now, getting back to the photovoltaics, as I explained before, a photovoltaic, if we're dealing with the microwave region, is an antenna array called a rectangle, and that has been experimented with at JPL, maybe many other places, I suppose, where they've successfully transduced the electric power in a microwave beam to DC power with 82% efficiency. And if you go through the physics of the thing, it makes a lot of logic, because light is for example, if my arm is a ray, the electric vector is at right angles to it, like this pencil. It could be anywhere, it could be this way or that way. What makes it polarized is they're all lined up in one particular direction. That's polarized light. Now, if we have the electric vector, say, pointed vertically, and we have a series of conductors which are also vertical, there will be an electric current induced in these conductors. So the electric field of the light induces an electric current oscillation in the conductors, the antenna, essentially. Now, when I perceived this idea, I then started looking into I did a literature search, and I wasn't surprised to find that nature had invented this thing 2 billion years before me. That the green plant is producing, has a molecular antenna in it. It's a carotene, which is a conjugated carbon chain of about 15 to 20 carbons. And then one end of the chain is connected to a donor and an acceptor, and there's insulating space in between. It's what is known as a tunnel diode. And so what nature did was take a molecular antenna and a molecular tunnel diode, put them in series, and produce an electric potential from a photon of light. And the photons of light that come in from the sun in visible range and nearby run from about 1.5 electron volts to about 3.1 in the Bravo. Now that's exactly a wonderful range for a photovoltaic system to start with, particularly since you can put them in series. And nature actually has put these antenna systems in series to split carbon dioxide into oxygen and carbon. They need a little bit more than 1 volt, and therefore they have two of these systems in series in the chlorophyll molecules in the plant membrane. So it has all been worked out before, but how to do it in a production way, and I wasn't interested in using the output electrical power from these minute antenna diodes to run a small-scale chemical factory in the cell, which is what gives us the energy to produce the proteins and the hydrocarbons, carbohydrates, and whatever the cell manufactures for its own use. But that's all an electrochemical process, which is powered by an antenna diode system, which is built into the cell of a green plant. Now, without it, we wouldn't be here. That system definitely exists. You can go out and check it by just looking at green plants, or even you got one on the table over there. So that system is right before us, before our eyes. Now, the problem is, let's duplicate it and re-engineer it for our own use. And that's where my work comes in. So I have made these proposals. I started working on it in my own laboratory. It turned out to be a rather difficult problem. First, I had to make a conductive polarizer. We succeeded with that. And by the way, along the way, I gave a talk on this thing a long time ago. I started on it 12 years ago. About 7 years ago, I gave a talk before the mid-area power pool group of executives from the power industry in the mid-portion of the U.S. About 200 companies who gathered together they have an annual meeting, and I was invited to one of them, gave a talk, and while I was there, a representative of the Electric Power Research Institute was there, and so he came over after I had my talk. He said, "Why don't you contact us? We're interested in funding you." So I said, "Wonderful." So then about 6 weeks later, I got a letter from him saying, let's make a submission, a proposal, which I did. But the money didn't come forth immediately. The contract was full of problems from a legal point of view. We would have ended up giving them rights to the patents and so forth by accepting their money, which we refused to do. It took them 2 years before they could resolve the matter. We finally did get a contract from them, and they put up $200,000, $100,000 for us, $100,000 for Lowell University in Massachusetts. We did as much as we could. We came up with a conductive polarizer, and that's as far as we could get. We didn't get to the diodes, the donor receptor complexes in there. Actually, you know, it's like having wanting to build $1 million house and you've got $100,000. It's not possible to do it. You've got to raise additional money from time to time, which I did, but still never enough. About 2 years ago, we were made aware of the work that was being done at Argonne National Laboratories under Dr. Michael Wasilewski. He's one of the premier photosynthetic scientists in the world, basically. He has a laboratory at Argonne, which is devoted exclusively to photosynthesis. And they've done some tremendous work. They published maybe 100 papers. And so I met with Dr. Wasilewski. He sort of liked what I was doing, and we eventually ended up with a credit with the Argonne National Laboratories, which provides essentially that the Department of Energy will put up $300,000 a year for 3 years. So they've pledged $900,000 to this, and we have to put up an equal amount, which is a strain on our meager resources, but we've been doing it so far. So that's where we stood. Then about 2 years ago, we got a couple of people came in. They said they were from the DOD. And they said they were interested in my Lepcon technology because they were working in space power, and they needed a material that would stand up for 30 to 50 years in space. And of course, plastics wouldn't do that, and probably existing photocells wouldn't do it either. So they wanted to see what I could do with the Lepcon concept. So they gave contracts to 100,000 last year they gave $100,000 to Cornell, $100,000 to Texas A&M. And Texas A&M, they both wrote wonderful reports. The agency that put up the money also put up $50,000 for advanced research, my company, to do the consulting and assist in the direction of the project. They're both deemed to be a success, but the biggest success was achieved by Texas A&M, who reported a direct conversion of light to electric power using an antenna diode. And they consider that to be a real breakthrough in science, which they have a letter from them, I think, which I've made available to the people here at the last meeting last night. So that is the story behind it. Now I want to, we're still in the position where we have to raise a great deal more money in order to carry this technology forward. Now remember what I said at the beginning of this discussion. First, that we're in a stage of development in photovoltaics where we have beginnings of commercial success, but it's being done with a technology that must be improved by in a basic way, not just by incremental improvement, but by totally new concepts. This concept I have has the possibility, and the scientists that have looked at it will agree that it has the possibility of 80% efficiency and very low cost, because it's nothing but a piece of plastic with very thin cast film on it, and there's nothing very exotic in the construction. The chemicals involved are fairly straightforward. Problem exists in the chemistry at the present time, and in fabrication you have to make the electrodes and do all sorts of things, run testing and whatever. It takes a large staff and a lot of capable people to do all this. So that's where we are at the moment. I'd like to just spend a little time with the view graphs I have, so that you can get a little better feeling for what I'm doing. So if you'll bear with me, I'll start with the graphs. Very short. Okay. Now this is too technical right now. We'll just stop this. Just show me the This is the basic concept of a femtodiode. This is a somewhat imaginary photon coming in. That's that black spot, and the electric field is, as you can see, is right angled to the light ray. The light ray is going down vertically. Now, this metal strip here, which is marked as number 1, is actually metal crystal, which is elongated. And the photon comes in, will penetrate the metal, and you know the metals are transparent to a small depth, about 50 angstroms. So the photon will go inside the metal, and inside the metal, there's a cloud of free electrons. And the photon reacts with the electrons, causes them to move along the strip, either to the right or to the left. If it moves to the right, comes up against the wall, where there's what is known as a work function electric field, electric barrier there. It just bounces off the field like a ball would bounce off a wall. And so then it goes to the left. And this is your tunnel diode right here, at number 3. The tunnel diode is nothing more or less than the space, and the walls of the facing metal surfaces are coated with a donor or an acceptor layer to 1 or 2 atoms deep. The effect of that is that the electron can pass through that. It's like a semi-transparent wall, like a ghost walking through a wall, so to speak, and ends up on the next metal piece here. Now all of this is connected through a load, and the electron has to do work in crossing this gap, the gap number 3, and that's where the energy of the electron is converted to work. And the work appears as a potential difference across the barrier. And that is used to drive, that's your basic photovoltaic cell. Now, if another electron comes in at the bottom there, 15, as a thermal electron, which has about, the metal, the free electrons in the metal are about 0.01 electron volts, and that's due to the temperature, their temperature. And this electron 15 is very low energy electron that's present in the all metals. And that'll simply take the place of the electron that's lost. So your connection goes, say, between 15 and number 2, and the load goes across that. But you can put many, many of them in parallel, okay? In parallel series.
What's the forward voltage drop across the front of the diode?
About 1.5, between 1.5 and 3 volts. Let's see, now, this one. Yeah, let me show this thing. They want me to just make a short presentation. This shows the charge pattern technology that I developed. On the top is just a non-charged surface, so for example, highly polished glass, and then figure 31 shows negative charges on the surface. It's simply negative electrons, negative atoms such as fluorine attached to the glass. And then the next one is possibly positive ions, could be hydrogen ions. And then down below, you see a charge pattern in figure 33, all in plus and minus areas. And then down below, just minus areas or plus areas. Now, the significance of that is that if you had a solution, for example, of a metal ion in a fluid, the metal would have a positive charge, would be attracted to the negative ions, it would deposit it only where the negative ions exist on the surface. So that way you can produce a pattern using electron beam on a surface by creating a charge pattern, and then subsequently you can use the charge pattern and simply wash it with a solution to produce your metal film in the charged areas, suitably charged areas. Okay, next one. Now, the interesting thing is that if you have an antenna array, okay, this is how you get the high efficiency from 2 polarizers. I showed you the polarizer that we had before, this one here. Now, that will transmit about 40% of the light, and that's for almost 100% polarized light. And so if we had a polarizing element there on the upper layer, say this, the upper plate at figure 14, we're at figure 14, and the lower plate was at right angles to it, like this. About half the light would be absorbed in the first one, and a little less than half in the second. So you would have all the light absorbed by the polarizing medium. But instead of being absorbed and lost as in the polarizer, it would be converted to electric power, and you get theoretically the maximum of half the electric power from the first level, other half again from the second, minus the losses, which I figure might be 10% in each sheet, and therefore you could end up with 80% efficiency. Now, the cost of this thing, from the point of view of a semiconductor material, is ridiculously small. If you make a polarizing material, and we've made it for 50 years so we know what the costs are, it costs you about $1 square foot. And therefore, if you need 2 of these, it's $2, and figure the electrodes are another $2, and packaging, whatever, $1, you got $5 per square meter, per square foot rather. Sometimes it's a square meter, forget the square feet. On a square meter basis. If you got, say, 250 watts from 500 watts of peak power from the sun, you would then have a cost of the order of pennies per watt. And I think that's the other one other thing I'd like to show you. Okay. One more thing. This is a diagram of a production unit that we have for making polarizing materials. You can use the same type of machinery and equipment for making these new photovoltaics.
Very much. Yeah.